All right, let's get started. So today I want to start talking about, uh, well, this is not a new system I'm going to introduce, but we're going to look at a different way of making the system move, or different way of exciting the system, as we call it. So far, well, we saw spring mass system, we saw spring mass damper system, we saw a pendulum, we saw systems that are mixed, like a bar that is rotating, and it has dampers and springs. We can either use the displacement as the coordinate that we can use, or the coordinate that we can write the equation of motion based on that, or we can use the rotation. We typically use the rotation. But in all these systems, one thing was not changing, and that one was initial conditions. If you remember, whenever I talked about the spring mass system or a pendulum or a spring mass damper, I was telling you that, well, we're going to excite the system, give it some initial displacement or velocity, and just let it go. For a spring, I was telling you, let's just assume that we're going to stretch it and let it go. Let's stretch the spring by moving mass in one direction or the other with respect to the equilibrium point, and let it go. Or we both can stretch it, and then instead of letting it go, we can just push it, or pretty much giving it some initial velocity. Those were the types of excitation we were using. Pretty much giving some initial condition to the system, and then let the system go and oscillate by itself. And that's how even we define natural frequency. We said if we disturb a system from its equilibrium point or initial uh, point and let it oscillate, the frequency with which it oscillates is going to be natural frequency. But today we're going to start looking at the same systems, but in this case, we want to look at the force vibration, or in this scenario, meaning that not only we are giving it some initial conditions, like stretching this spring to some degree, or the mass attached to the spring to some distance away from equilibrium point, giving some initial velocity, but also providing some constant force applied to a system during the motion. So I'm not letting this mass go. I'm stretching it, and then I start pushing it back and forth while it's oscillating. So this force is constantly providing a source of energy to a system. Before, I was just letting it go, so the energy was dissipating if I had a damper, for instance, or if whether it was a viscous damper or it was a friction, it was friction in the system, they were oscillating, they were dissipating the energy of the system. Now, if I provide a constant source of energy, whether it's in the form of some applied force supplied to the system, or some kind of imposed displacement, I force this displacement. I say I want the system to be displaced following this specific pattern. Then we have a force vibration, as opposed to what we had before, which was called free vibration. Free vibration meaning no external force was applied to the system. Only initial conditions were given. So we start talking about force vibration, and from there you will see there are very interesting applications that are very relatable, I would say. Uh, we can study, or we can go further into details about them when we know force vibration and we know how to deal with a system under force vibration. So I'll start with force vibration. Force vibration. If I want to put in some put some words, I'll say a system uh, uh, undergoes force vibration, right? uh, if an external source of energy is supplied to the system during vibration. Now, this external source of energy can be either some force that I apply, right? Or it can be some imposed displacement. In terms of force, I would say apply, let's say, 20 Newton force constantly to the system. Or in terms of imposed displacement, I can say I want this mass to be moved, let's say, 2 inches away from equilibrium point constantly, and then 2 inches to the other side, some kind of imposed oscillating displacement to the system. So it can either be, let me just write it here, this external energy source or energy, let's put it this way, can be either some can be an applied force or can be an imposed displacement, depending on how I supply this energy. If it's an imposed displacement, I'm also constantly giving some energy to the system. I'm preventing this the energy of the system to totally dissipate, or the energy is still dissipating, but I'm compensating for that dissipation by supplying that force or displacement. Now, depending on the form of this applied force or imposed displacement, we're going to have different types of situations. This applied force can be just a shock. Right? I can just hit, think about a hammer. Right? I can just hit a spring mass system with a hammer. Right? Just hit it and then wait and look how it oscillates. I can apply this force as a sine or cosine function. I say, well, the same way that we saw the system was oscillating, I can say, well, I want this force to be 10 Newton, but these 10 Newtons be in the form of some harmonic function, like sine or cosine function. It can be neither of these. It can be just some random force. A very good example is earthquake. Right? When we have an earthquake, the building is shaking, so the earth, look at it this way, is providing some source of energy, some kind of applied force or some kind of imposed displacement to the system, in this case being the whole building. And the building is shaking, right? It starts shaking. The earthquake is probably for a few seconds, right? But the way it shakes, that imposed displacement or applied force is not harmonic, is not a shock, it's some random motion caused by some random force applied by the system. So depending on what type of force is applied to the system, what type of displacement is imposed to the system, we're going to have different situations. And mathematically speaking, there are ways to look at the system response, but those ways change depending on how we oscillate or how do we supply this energy to the system. So let me just briefly say this here. A few of these we're going to look into them in this course, but it's good to know. So this source can also be, let me give more room here, can also be, first case, harmonic. That is probably the easiest case to deal with. The force is in the form of a sine or cosine function. It can be, and I can just put something here to give you some sense of what I'm talking about when I say harmonic. Very similar to the plots, graphs you've seen, is whether it's a sine or cosine function. We have some force applied to a system which is very following a sine or cosine function. If this is force and this is time, we can look at it as harmonic. Example. Can be non-harmonic. And this non-harmonic can either be periodic or non-periodic. Right? I'm not gonna. I can just divide it, I guess, here. This could be periodic or not. No, let me just separate them. So let's say non-harmonic periodic. I can just put them in different categories. So it's not a sine or cosine function, the force that is being applied to the system, but it's still periodic. Right? What do I mean by that? Well, if I have a system, let's say some force is applied to it, let's say it's like this. This is the force, and then it repeats itself. Right? It's supposed to look the same. So it's not harmonic, right? It's not a sine or cosine function, but it is periodic. Right? One period here, another period, it just repeats itself. It's an example of non-harmonic but periodic force. The more general one would be a type of force that is non-harmonic and non-periodic. These are possible excitations that you can have in your system. And this example for non-harmonic and non-periodic, good example. Again, you probably hopefully you haven't felt it, but it's an earthquake. Right? It's totally random most of the time. Some random force is applied to the system, and it shakes the system. It shakes the whole structure. And it's non-periodic. It doesn't repeat itself. It occurs for a few seconds, and then some random excitation. You will see the record of that. Another example of non-harmonic, non-periodic would be an impulse input. Like that hammer that I told you about. Imagine that you just have an impulse. You hit the system at the beginning with some initial force. We usually show the impulse function as something like this. Small amount of, a huge amount of force in a very short period of time, and then we let the system go. It's also non-harmonic and non-periodic. Right? It doesn't repeat itself, and there is no time period there. So it's also not harmonic. So these are all possible, at least within the scope of not very advanced levels, or possible sources of applied force or imposed displacement to the system. Now, this course we're going to talk about, in this course we're going to talk about harmonic type and a little bit about non-harmonic and non-periodic when we look into systems under the excitation by an impulse or some random force. Non-harmonic periodic is not exactly what we're going to talk about here. All right, so this is generally a force vibration. Let's just focus on the first one, right? The harmonic type of excitation. And we're going to start with the simplest system that we're dealing with, right? The swing mass system. For now, let's just put damper aside. Don't be worried about damper. We'll talk about the harmonic excitation of a system with damper in next class. In this class, let's just be focused on harmonic excitation with no damping. Hopefully, so far, things make sense. Stop me if you have a question, right? All right. So let me put it under harmonic excitation with no damping. Quite a long title, but so I have my spring mass system here. Let me use the typical color. I have my spring mass system here, mass M. I don't want to deal with any friction, so just think about there is no friction, smooth surface, or there are wheels that we can ignore friction. Stiffness, it's a typical system we had from before. Now what happens is that I have this force applied to the system, and I show that force as F cosine omega t, which is a harmonic force. F naught cosine omega t. F naught being the amplitude, some newtons, like 5 newtons, 10 newtons, thousands of newtons, depending on the type of system we're dealing with and the type of excitation. And cosine omega t. Omega is just the frequency of this force. Right? If you want to plot this force, the supplied force is something in the form of this. We have F naught cosine omega t, so something like this. This is the force Ft over time, and this being F naught. It's just a function of time. This is constantly supplied to the system. Now I want to take a look and see how can we find the system response under this kind of excitation when there is no damping. All right, let's take a look at the free body diagram. All right, if I draw that here, this is going to be my free body diagram, mass M. Right, I still have Kx, and let's say system is going to write, I'm supplying this force, well, cosine omega t. And on the other hand, on the other side, hopefully if I'm making a mistake, stop me. This is M, and this would be mx double dot. Probably it's easier if I just put everything in the same direction. Let me just draw it and see if I get the equation. Otherwise, I'll fix the directions. So summation of forces is equal to whatever inertial forces I have on my kinetic diagram. If I write it this way, let me see, minus kx plus F naught cosine omega t will be equal to mx double dot. This should be double dot. So mx double dot plus kx is going to give you F naught cosine omega t. So that becomes the equation of motion. Right. Now I'm just going to rewrite this equation of motion a little bit. It helps us to get a better sense of system response when we write the system response as a function of natural frequency and frequency. So I'm going to, all I'll do is that I'll divide both sides of this equation of motion by m. So the first part becomes x double dot plus k over m. X is equal to F naught over m cosine omega t. Now from before, well, I know k over m is omega n squared. Right? Natural frequency was the square root of k over m. So k over m would be omega n squared. And I'll call this F naught over m F naught, lowercase f naught. So I can rewrite this equation as x double dot plus omega n squared x plus f equal to F naught cosine omega t. And this would be the equation of motion I'm going to use. From the original equation of motion, I just divided both sides by m. So this would be my equation of motion. Keep in mind, this happens a lot in this part of the course, that you guys, some of you guys get confused between omega and omega n. Omega n is the natural frequency of the system. Has nothing to do with the external force. No matter what external force you apply to the system, or whether you apply external force or not, omega n doesn't change. Right? It's just a natural frequency. natural frequency. Omega, on the other hand, is called the frequency of excitation. That's the frequency of the force, harmonic force applied to the system. Frequency of excitation. So these two are two different things. Omega has nothing to do with what the external force is. Omega is related to the external force. If there is no external force, obviously that's zero. Depending on what is the time period, as I plotted here for the force versus time, obviously the time period and frequency of that force dictates what that omega is. So now we have an equation of motion for this system. Second order differential equation. Right? We have to solve this. Now, how much, depending on how much you remember from differential equation, the course you had, it makes it easier for you to follow what I'm about to do. If you remember, let's put it this way, if you remember how to solve a or better to say, non-homogeneous second order differential equation from the course you had, you're going to have a pretty easy time to follow what I do, hopefully. If you don't be too worried about it. Just try to follow as much as you can. It would be great if you follow every step that I do. That's my intention. And I'm hoping that it happens. But I do understand some of you had this course a while ago, so some things might be fading, kind of. So it's a second order differential equation. We saw the left side before. If you look at the original equation of motion, mx double dot plus kx for a spring mass system, the right side was 0, so mx double dot plus kx is equal to 0 for a spring mass. Now we have a force. The force is on the right side. It's not 0 anymore. Now looking at the modified equation of motion, again, just the same thing. Right? The left side is the harmonic side. The right side is homogeneous side. If the right side is 0 and the extra part that makes this equation of differential equation non-homogeneous is f naught cosine omega t. So for this non-homogeneous second order differential equation, the system response would be, or the response or the solution to this differential equation has two parts: homogeneous part and particular part. And particular solution is the solution that is coming into play because of the non-homogeneous part of the equation, f naught cosine omega t. Remember when we were talking about how to solve differential equation second order, we had this term, and depending on what is the form of that non-homogeneous part, f naught, in this case it's a cosine function. Depending on what is the form of that, we had some suggested solutions. So homogeneous part is what we have from before. Right? It's not new. We saw it when I was talking about Coulomb damping, for instance, more recently. I said we just put some constants. Right? It's in the form of a cosine omega n t plus b sine omega n t. That's the general form of the harmonic part of the homogeneous part of the equation, assuming that there is nothing on the right side. And a and b being constants that we have to find from initial conditions. Now, what is added is the particular form of the solution. A particular form of the solution, the general form of this solution, is dictated by the form of the particular part or non-homogeneous part, which is f naught cosine omega t. Since it's a harmonic function, I'm going to say, well, the suggested solution should be also a harmonic function and in the similar form. So I suggest the solution of x cosine omega t. Pay attention. Harmonic part or homogeneous part. Sorry, I don't know why do I keep saying harmonic part. The homogeneous part has omega n. Particular part has omega. Omega is the frequency of excitation. Now, I have another constant x here. X is also a constant I have to find. Can anyone tell me, does anyone remember how do we find this x? Or the constant in particular solution. Yeah, early morning, a course that you took probably 2 years ago, a year ago, 2 years ago. Doesn't help, I guess. All right. So to find that x, all we need to do is that, well, this particular solution is still a solution to this differential equation. So if I plug this back into my equation of motion, that second order differential equation, it should hold true. It's a solution, it's particular solution, meaning that it's just for a specific case, but it still holds true. So I'm going to plug in, I'm going to put a note here to find constant x, plug in, I don't want to say I, plug in x into equation of motion. Sorry, xp. So if I do that, take derivative twice, that becomes minus omega squared x cosine omega t plus omega n squared x cosine omega t is equal to f naught cosine omega t. Pretty straightforward. Cosine omega t, cosine omega t, cosine omega t. So f naught, or x, becomes f naught over omega n squared minus omega squared. Here is x. I found my constant x in particular solution. Now if I plug this in, everything together, right, xt becomes a cosine omega nt plus b sine omega nt plus f naught over omega n squared minus omega squared cosine omega t. Now this is the general form of the solution. General form of the solution. Now what I'm missing now is our A and B. Right? These are coming from the general form or suggested solution for the homogeneous part. To find A and B, I'll just use initial conditions, right? Very similar to what I was doing before. Now I have a particular part that everything is clear about that. I know it's cosine omega t, and the constant behind in the back of that is f naught over omega n squared minus omega squared. To find A and B, I did what I was always doing before, using initial conditions. So let's do that. So using initial conditions to find A and B, use initial conditions. What are initial? Owen, do you have a question?
Yeah, I was going to ask you to go back for 1 second.
Sure.
That's good, thank you.
Good. Okay. So initial conditions. Right, I just take x at t equals to 0 as x naught, and x dot t, x dot as t equals to 0, x dot naught. Some initial displacement, initial velocity. Now if I plug in t equals to 0 to the general form of the solution here, the first one becomes a, plus the second term becomes 0, and the third term becomes f naught over omega n squared minus omega squared. So this gives me, the first one gives me x naught is equal to a plus f naught over omega n squared minus omega squared. So a can be found as x naught minus f naught over omega n squared minus omega squared. This is A. To find B, I have to take derivative and make it, plug t equals to 0. If I take derivative with respect to time from this general form of the solution all the way at the bottom, the first term gives me sine omega n t, so it becomes 0 at t equals to 0. The second term gives me b omega n cosine omega n t, so it becomes bn. The third term, we are going to get another sine, so that also becomes 0. You can do it yourself and double check. This becomes b omega n. So from there, b becomes x naught dot over omega n. This is the second constant. I found a and b. Right? It's pretty much what I wanted. So the general form of the solution, right, now becomes, let me try to write it here. xt becomes, I don't know if I can fit it there. Let's just not be stingy with the space and just write it. xt would be a, which is now x naught minus f naught over omega n squared minus omega squared. Right. I forgot what was the first term. A cosine omega n t. So this is cosine omega n t plus b, which is x naught dot over omega n sine omega n t plus f naught over omega n squared minus omega squared cosine omega t. So this is the general form of the solution. System response. So if I know f naught, which I know in this case, I can find f naught by knowing uppercase f naught, the amplitude of the input force, and the mass of the system. I can find that. Omega is the excitation frequency. Omega n is the natural frequency. X naught and x naught dot are initial conditions. So once I know these, I can find what is the system response. How does the system respond to a given harmonic excitation in the form of f naught cosine omega? Now, keep in mind, do not get confused between this f naught, the other f naught. You are usually given the other f naught, like the uppercase in the unit of newtons or any unit for force. You have to divide that by m to get this f naught, lowercase f naught. Don't get confused with that, between these. All right. So far, so good. Now, of course, that's not going to be the end of story, right? Would have been great if it was. Now, there are two special cases we have to look at, which one of them is very important, and you hear that term and that condition or that situation. I talk about that situation over and over for the rest of the semester, or at least for the next couple of weeks. So case one is when this system response, what happens in when omega and omega n are the same? What if, right, if this case is the case if omega is equal to omega n, right? It can happen. The frequency of excitation, whatever it is, can be the same as natural frequency. Now, if you look at the system response, we have two fractions there, f naught over omega n squared minus omega squared. Right? That fraction is appearing in two terms. Now, the problem happens. The problem is the denominator becomes 0. So this solution doesn't hold. It becomes infinity and doesn't make sense. How can I plot this, or how can I use this to show the system response? So mathematically speaking, this happens because the particular solution that we chose here x cosine omega t becomes also the solution, right? I don't know how much you remember from differential equation, but that particular solution becomes also a solution for the homogeneous part. And what we should do is that when we choose a particular solution, the solution for the particular part or the particular solution should not be a solution for the homogeneous part of the equation. You always avoid that. If it happens, that's not the right type of solution, or general form solution to choose. So when omega is equal to omega n, this xp t equals to x cosine omega t is not a correct suggested solution or particular solution. So what do? We have to provide a new suggested solution, right? Let me put it this way. X cosine omega t becomes a solution for the particular, for the homogeneous part, homogeneous part. So we need a new form of particular solution. And we're going to choose it as xpt as xt. Let me double check my notes. Yeah, I choose it xt sine omega t, right, instead of that x cosine omega t. And most of it goes back to differential equation. But I don't want to go through the whole process again. If you do this, plug it in, find the coefficients, everything holds up, right? If you use initial conditions again to find A and B, the same process, you will get the general form of the solution in this. You'll get x naught cosine omega t plus x naught over omega n. This part doesn't change. Well, sine omega t plus, now you have f naught over 2 omega t sine omega t. Can be found again this following the same process. First, you plug in the particular part into the equation. You'll find f naught over 2 omega as the value for x, and then put everything together and apply the initial condition. So this becomes system response for this special case when omega and omega n are the same. Now this was the explanation in terms of mathematics. But physically speaking, what happens? That's the important part. Physically, when omega and omega n are the same, we are going to have a situation that the amplitude of the vibration goes to infinity. It starts oscillating more and more and more. The amplitude keeps increasing until it goes to infinity in terms of like abstract thinking. And if you want to think about the structure breaks. Like if I have a column that I'm going to excite that column or a specific part of the machine that I have, if being excited by its natural frequency, the amplitude increases a lot. Like in this case, we don't have damping, so it goes to infinity. But at some point, this increase in amplitude is going to break the system. If you want to take a look, for instance, at the plot, if this is the system response, let me just do it here. If this is the system response, when omega is equal to omega n, that's what you, let me draw these two. That's what you're going to see if you measure the displacement. Keeps increasing. So this is xt over time. This line you see here is that coefficient that we found, f naught over 2 omega. Well, t, since it's a line. Now, this is called resonance. Resonance see if I have a good definition for that, or I can just put it here. It occurs when the frequency of excitation is the same as the frequency as the natural frequency, as the natural frequency. Right? Omega becomes equal to omega n. It's equal to omega. It's a very important concept. When we design something as engineers, we really always have to take that into account. Omega n is the property of the system, depending on how heavy that system is or that part is, and how much is the stiffness. So it has some natural frequency, omega n. Omega is the frequency of the force. Depending on where you are going to use that part in your system, is there going to be a force which its frequency is close or equal to natural frequency of this part? Then it's a problem. So you need to know the natural frequency of your system, whatever part you're making in a mechanical system. And you need to also be aware of possible forces that are going to apply to your part or to your structure, to your machine during its operation. And to make sure that they don't get close. Specifically, they don't become the same. If they do, then the structure is going to break because of the huge oscillations we're going to see. It's not going to hold up. So resonance is a very important concept when it comes to designing systems. And a lot of finite element softwares, commercial packages, non-commercial packages can do that for you, and they can find natural frequency of the system, so you know where the resonant natural frequency is, to make sure that whatever is the operating condition, the force in that condition is not does not have a frequency close to your natural frequency, so you don't have resonance. We are talking about, we'll go further in the rest of the semester, talk about systems with more degrees of freedom. In this case, we only have one natural frequency. When we have systems with more degrees of freedom, there are multiple natural frequencies. And again, that's why when you do some analysis in some finite element software, you will see multiple natural frequencies, 10, 20, 30. In those cases, when we have a very huge structure, we have not infinite, but equal to the number of degrees of freedom in your structure. We have natural frequencies. So in this case, in simple system, there's only one. But when you design shafts, specifically, the first natural frequency is very important, or as we call it, the critical speed, same as natural frequency. Critical speed of a shaft is its natural frequency. So you have to make sure that when the operation, this operation speed of that shaft, whatever it is, right, is way away from its critical speed. Right? Replace critical speed and operation speed with natural frequency and frequency of the excitation. These are the same, just different terms. And that's why you always design a shaft, make sure that critical speed is not close to the speed of the operation. It's the same concept, resonance. You want to avoid resonance, because if you do, then the shaft starts bending up and down hugely. All right. So that was case one, right? When omega is equal to omega n. And there is a second case, less important, but it's still interesting, that when omega is not equal to omega n, but it's very close. So I have a mess of colors. So case two, this happens when omega write it better. When omega is not equal to omega n, but it's close to omega n. What happens here? We're going to have beating phenomenon. It's called it like a beating, like heartbeat. Right? So I think the name comes from that. Now, for a special case, I can give you even the system response, and from there we can get some insights about what happens. Right? For the case that x naught is equal to 0 and x naught dot is also equal to 0, I can give you the system response. I actually have it here. System response will become 2f naught over omega n squared minus omega squared. And I can rewrite the system response I get from the general form in this shape as a multiplication of two harmonic functions. And omega n plus, I'm not going into details about this. We mainly care about the physics of what happens. And this is the multiplication of two harmonic functions. Again, this is called beating. And why do we call this beating? If I plot this response like this here, and let's see how accurate I can get. I'm gonna have something like this. I can do a little better than that. This way. And then there is, I just want to identify the envelope. So the system response, if I plot that xt, this is xt over time, would be something along this line. As close as I can get. It's getting more and more ugly, but so this continuous line is xt. Now, if that is xt, let me extend this line a little bit. If that is xt, this maximum amplitude here, right there, is this coefficient. So this is f naught over omega n squared minus omega squared. What else? I have a multiplication of two harmonic functions. So one of them is enveloping the other one, mathematically speaking. So this envelope here, the equation for this is 2f naught. Let me just put it on the top one. For this, we have 2f naught over omega n squared minus omega squared. I need more space here. 2f naught over omega n squared minus omega squared sine omega n minus omega over 2t. This is this envelope. So the first term is a term with very long time period. Right? First term, I'm talking about this term. If you look at the frequency here, omega n minus omega over t, omega n and omega are very close to each other. So this is the numerator is a small number. So omega is very small. So when omega is by omega I mean, let's call this omega prime. This omega prime is very small. If omega prime is very small, it means the time period for this part of the harmonic motion is long. And that time period would be this. You can actually plot it here or show it here. This would be the time period. One motion, right? It goes from here, one cycle of the motion, all the way to here. So the time period would be this whole thing. Now we define something, since it's called beating phenomenon. Let me add it somewhere. This is called beating phenomenon. Right. Now, we define omega beat. This is just a definition as omega n minus omega. Case 2 is beating. So case 1 was resonance, case 2 is beating. If you use that one, the time period you get here would be 4 pi over omega beat. You can do the math and figure that out. Omega n minus omega, if I take that as, imagine, remember this specific line is just the first part of the equation. 2f naught over omega n squared minus omega squared sine omega n minus omega over 2t. Omega n minus omega, if I take that as omega beat, let me see if I can, I'll just quickly put it here, but I will not, I'll erase it. So this is the frequency for this part, or the envelope around connecting the peaks. If you take that as omega, right, t would be 2 pi over omega, right? Omega prime, that's it. So that would be 2 pi over omega n minus omega over 2. That gives you 2 pi or 4 pi, 2 comes up. That gives you 4 pi over omega n minus omega. And omega n minus omega, I defined as omega beat, so that's where you get this 4 pi over omega beat. Time period for the envelope. I'm going to erase this later on, it's making it messy. But now the time period for the motion itself, for the response itself, pick any two peaks, that will be 4 pi over omega n plus omega. So this part gives the oscillation with short time period. The first part, the orange part, gives the oscillation with long time period. Right? It's not exactly the oscillation, but for the response we get. No, it is an oscillation. So when you're given the beating system, let's say response, first of all, by looking at it, you can see it's beating. Omega and omega n and omega are close to each other. And secondly, you can identify different parameters. let me just erase this. It's just the logic, so you know where did that orange time period come from. All right, that's pretty much it. Right. I just I can give you some where to look for examples before I do my go over the example I want to go over in the textbook. Look at I'm gonna write it here. Look at examples for the force vibration. 1.1, 2.1.1, 2.1.2, 2.1.3, and actually 2.1.4. These are good examples in the textbook related to the topic we covered today. I do have an example, not in the textbook, so let me go over that. Before I start looking into example, any question? I always, when I teach vibrations, I know that it's usually in the morning, a lot of math involved, but I always ask you guys that do not get distracted by the math. Like, this is, the math provides a tool for us that we can solve the equation of motion. We can see physically what happens. You know, what is the system response when it's under harmonic force excitation with some given initial conditions and properties of the force. What happens if omega and omega 1 are the same? Resonance happens. So physically, we have to be very cautious about that. What happens is they're close, beating happens, right? Just keep in mind that you get insights and you use math to overcome the or to solve the equation of motion and get the system response. So from there you can get insights. And you know, it's good to follow the math. I honestly, there's nothing here that you have not studied before. I know some of it you forgot, which is not unusual if you haven't used it. But everything we say, you have studied before, hopefully, even mathematically. But don't be distracted by the math. Understand the math, follow the math, and see how we get what we get. It's very important. But at the same time, keep in mind you're engineers. Math is a tool. Math is not the destination. Right? It helps you to get to the goal, which is to get to know the system, how the system reacts, what happens if different things happen, how does the system respond to this kind of force, right? All right, let's look at this example. Relatively long, but in terms of problem statement rather than, I'll try to summarize it. So we have a reciprocating pump. It's a very practical example, and that's why I always reciprocating pump. With a mass of 75 kilograms mounted on it says at, so mounted at the middle of a steel plate of thickness 13 millimeters with I think it's 500 millimeters and length of 2.5 meters, clamped along two edges. So this is trying to say that here is we have a plate, something like this. Not that. I'm gonna move this over here. It's clamped on both edges. I'm just looking at it from one side, obviously. We have a reciprocating pump sitting exactly in the middle. I'll try to draw the pump. This is the pump. Middle of it is a reciprocating pump. So if it's a piston and cylinder, it's connected, let's say, to some, and it's rotating this way. So the piston goes up and down inside the cylinder. And because of this motion, when it goes up and down, it's applying some force to this beam, to this plate. Now the question is, once the pump starts, operating, the plate is subjected to a harmonic force in the form of Ft is equal to 250, which is F naught, cosine 62.8 Newton. That's my input force. Now I'm asked to find the response at the center of the plate, at the center, if we can consider it as a beam. And you're giving the property of the beam also. E is equal to 200 gigapascal. All right, so it's a plate, it's fixed on both edges all the way, so it's asking us to look at it just as a beam. So we can use what we learned from before, that we can replace this beam stiffness, if you remember, with this spring. We know this excitation applied to the middle of this beam. We are given that, right? I'm not going to rewrite it here. It's 250 cosine 62.8 t. So the first step I do is that, well, I have to go to a system that's familiar to me. Right? This happens when you're doing a design. You have a pump somewhere sitting and you want to figure out how does this beam react? What is the response? How much is the bending, if you think about that in terms of solid mechanics? How much is the bending in the beam when this pump is operating? And from there, knowing the force, we can even do calculations for fatigue life and predict what kind of material you need, etc., etc. But let's just stay within the scope of this course. So Ft. Now I want to find the equivalent of this. Hopefully you remember from stiffness. If this is a mass, it's a spring fixed there, and then I have some force applied to it. Right? This is nothing but call this K equivalent, my spring mass system. Right? It's a totally different problem, but I can easily boil it down or simplify it to a spring mass system with a harmonic force excitation. So the first task would be find a K equivalent. And K equivalent for this one, it's a clamped beam, and we're finding a displacement in the middle, or we are interested in this deformation in the middle when the force is applied in the middle. If you go back when we talked about stiffness, that's one of the cases we talked about. We said the equivalent stiffness would be 192 EI over L to 3. I have to find a couple of things. I need to know I I'm given the information about the cross section. I said the thickness, I'm told thickness is 13 millimeters and width is 500 millimeters. So the cross section, I know the width is 500 millimeters. I ignore the unit for here, make it more clear, and this is 13 millimeters. This is a rectangular cross section. The moment of area, hopefully remember, again, goes all the way back to statics even, and solid mechanics. Let me write it here. I is 1 over 12 BH to 3. Right? In this case, B would be 500 millimeters, so I'm going to put 0.5, stick with the unit meter. And 13 millimeters, I'm going to put 0.013 to 3. If you do this math, you will get 9.2 10 to minus 8 M4. Right? This is going to be your E, or your I. E is given, modular velocity 200 gigapascal. So I can calculate the equivalent stiffness. 192 times 200 times to 9 times 9.2 times 10 to minus 8 divided by, and I'm given the length of this, 2.5 meters. Right? So 2.5 to 3. Doing this math, you will get 6.1 kilonewton per meter. If I didn't make any mistake, this should be the number you get. Let me know if I made a mistake so I can fix it in my notes. So the rest is pretty straightforward. Now you have a mass, right? When going from the reciprocating pump that is applying this force, now you know the input force. You have a spring mass system. You want to find the response of this spring mass system to this given input harmonic force. All you need to do is to find the components that you need for that system response, right? If remember the system response in general, maybe in this case you have to find natural frequency first and see if natural frequency is close to the frequency of excitation. The frequency of excitation is 62. This is omega, and this is F naught. Right? This is F naught cosine omega t. It's a type of excitation we saw before, or that's the type of excitation we used for analysis. So if you find omega n would be equivalent of stiffness over m. So that'll give you 226.1 times 10 to 3, which is because it's kilonewton per meter, and the weight of the pump is given as 75 kilogram. That gives you 54.36 radian per second as natural frequency. 54.36, that one is 62.8, so you're far enough. In terms of beating, how close you should be to get beating, a little tricky. But keep in mind that for beating, the system response does not change. The general form is still the same. I just rewrote that for a special case so we could take a look at what does it look like and why do they call it beating, or at least what is the form of it. But generally, XT is the same for beating. The only time that XT changes or system response changes is when we have resonance, because that mathematically doesn't make sense. So to get the system response, I'll make it short. We have F naught, obviously, as 250 Newton. We have M as 75 kilogram. We have K, which is K equivalent now, is 226.1 kilonewton per meter. And we have omega, excitation frequency, 62.8 rad per second. So from these two, you can find F naught. Remember that we need F naught. So it would be lowercase f. That will give you F naught is 250 divided by 75. Again, if I'm not making any mistake, 3.33. Now the tricky part is We know everything, but if I want to write the system response here, so the system response, I need a little bit more, right? We had F naught, we had X naught minus, we had xt in the form of X naught minus F naught over omega n squared minus omega squared. Hopefully I'm writing it correctly. Cosine omega, I might not be writing it correctly. Let me double check. Yeah, cosine omega nt, and the next one is sine omega nt. Cosine omega nt plus, right, X naught dot over omega n sine omega nt plus we had F naught over omega n squared minus omega squared cosine omega t. Right? That was the system response, general form. Now the problem is we have everything except initial conditions. How do we find initial conditions? The pump is sitting on this beam. So there is no initial velocity. I turn on the pump, it starts creating this harmonic force in the beam. So no initial velocity. That I'm good. Right? If I put initial conditions here, initial velocity is 0. How about initial displacement though? How do I find that? The pump is sitting on the beam. So do I have an initial displacement? First question. It's the last piece of this problem I want to decipher. The rest is straightforward, just plugging in the numbers. Now, when this pump is sitting on this beam, obviously we're going to have some initial, right? Think about this, M, and then this is K. So wherever it was before this, wherever this beam was, we're going to have some initial deformation, right, because of the weight of this beam. And that initial deformation would be the initial displacement. Tricky, right? How do I find that initial deformation, which is going to be initial displacement for my system? Well, I know the stiffness, right? F is equal to kx naught, or W in this case. Let's just write it in the general form. F is equal to K equivalent x naught. So x naught would be the weight of this. This F would be the weight, so 75 kilograms times 9.81 over the K, 226.1 times 10 to 3. If you do this, you will get 3.254 times minus 3 meter. So now you got your initial velocity and you got your initial displacement. Initial displacement came from the fact that this beam, which I'm replacing it with the equivalent spring, is stretched a little bit because of the weight of the pump. The rest, pretty straightforward. Now you have x and x naught. You have x naught and x naught dot. Go back to the general form of the system response. You have f naught, you have omega n. Just replace them. If you do that, you will get the system response. I'll give you the general form. 3.25 10 to minus 3, which is the initial displacement, times, or I would say minus, I guess it has to be minus, yeah. Minus 3.33 divided by omega n, which is 54.36 squared, minus omega 62.8 squared, cosine 54.36t, plus the second term becomes 0 because x naught dot is 0, and the last term would be 3.33 divided by 54.36 squared minus 62.8 squared, cosine 62.8 t. This is the final answer. This is the system response. So, as simple as it looks, we just study a spring mass system under harmonic force. We can easily use that for practical problems when you're doing designs. And believe me, these are not something unusual. Even when you want to do design, the initial calculations, you can just use very simple models to get a sense of how much force, what is the system response, how it's going to work. Later on, you can go into more details, create a whole model in some fancy software, and do the calculations. But here is you get a sense of how does the system operate. All right.